In this question here, you're being asked to circle the most acidic compound from each of the series below. Provide a rationale for your pick, either electronegativity, resonance, induction, atom size, hybridization. All right, so as you probably heard me say in a few of the previous examples, when you're comparing the acidity of different compounds, don't even look at the acids. Look at the conjugate bases and then compare the stability of those conjugate bases, all right? So the first thing we want to recognize is which atom on each of these is going to be the most acidic. So is the hydrogen going to get ripped off of this carbon or this one or this one for the first species? Is it going to be here, here, or is it going to be this one here or here for that species? And then, or is it going to be here, here, or here for the third one? Right? So we can show the conjugate base for each of these. So for the first one, I'll show you all the possibilities. Okay. So we can either have the negative charge here, we can have the negative charge here, or we can have the negative charge here. All right, now for those first three, we want to figure out which one's the most stable. The negative charge is on carbon in each of them. The hybridization is the same, so there's no difference between that. What is different is the ability to have resonance, okay? So this one here, those electrons, they're just stuck on this carbon here. They can't move around. They're too far away from that carbon-oxygen double bond. So it's not going to be this one here, so I'm going to cut that one out. Now these two, they can have resonance, okay? What I mean is these electrons could move here and kick those electrons up there, and that's going to form this resonance structure, okay? And this one here can move those electrons there and kick that up there, and that's going to form this resonance structure. All right, so they have the same amount of resonance, so they're pretty equal in stability. They're probably going to have a very similar pKa value for each of those. But one is going to be more stable than the other. And we can kind of think about that by saying, all right, well, which one's handling the negative charge the best? So in this one, it has that negative charge there, right, on a primary carbon. But here it's on a secondary. Well, here it's on a secondary carbon. Remember, that methyl group is going to be inductively donating there. So that's going to make that negative charge feel a little bit more negative, which that's going to destabilize it when it's on the carbon in this structure. So it's a little bit more destabilized when it's in this position. Okay, this one doesn't have any inductive donator groups to it, so it's a little bit more stable on that carbon, which means this one is not going to form most likely. All right, so let's cut that out there. There's other arguments that we can have to say this one is more stable. We're just not there yet, so we're not really going to get into that yet. So we're just going to go ahead and say that, this most accessible primary hydrogen of structure A is the most acidic proton. We'll do the same thing for B. So for B, we want to figure out what the most acidic proton is. Is it going to be a proton from this carbon on the end there? Is it going to be a proton here? Or is it going to be a proton here? All right, well, yeah, an sp2 carbon, it's a little bit more acidic than an sp3. But this one here, it has the negative charge localized. It can't move anywhere. There's no resonance. But these two have resonance, so that's going to help stabilize those, which means those protons are going to be more acidic because that negative charge is more stable. So we're going to remove this top one here because that's not going to form. Now, between these two, which one has the negative charge more stable? Well, this can engage in resonance here, which forms this resonance structure. I'm going to draw all these in. Okay, so a little bit of delocalization, but this one here has a lot more delocalization. What I mean is we can move the electron density over to this carbon here. And that was the result of these electrons moving here and pushing the electrons to this end carbon here, right? And that's what formed this resonance structure. All right, well, the electrons could have actually went the other way as well. So let me draw that resonance structure. And this is the result of the electrons moving here which pushes those electrons up there, resulting in this resonance structure here. So altogether, when you remove the proton from this carbon here, you get a lot more delocalization, which means these protons on this carbon here are more acidic for this molecule. So we're going to cut this one out. Cut. Move this up here. So now we're just really drawing the conjugate bases that are going to form here. Okay. Now in this third one, let's take a note. Instead of drawing all the resonance structures, we can recognize that, you know, if the negative charge ends up here, there's a little bit of resonance between here. If the negative charge ends up here, it's the same thing, a little bit of resonance. But if the negative charge ends up here, now we have resonance over all of these atoms. So what that means is you should be looking at this and saying these are probably the most acidic protons. So let's just draw that conjugate base instead of just drawing everything. All right, so let me draw the negative charge here. And of course, it can move around. It can go here and push that negative charge up there, or it could have went the other way and went here and pushed that negative charge up there. All right, well, now we can see these species B, whoops, not my highlighter, species B and C have the same amount of resonance. They have 3 resonance contributors. This one has 2. So this one has less electron delocalization, which means it's not going to be as stable, which means there's no way this thing can be as acidic. So it's definitely not this structure. Okay? Now, between these two, let's just compare the 2 intermediates and let's figure out which one is handling the negative charge the best. In B, that negative charge can exist on a carbon, it can exist on another carbon, and it can exist on an oxygen. Obviously, oxygen handles it best because it's more electronegative. It handles the negative charge better. So it exists on a carbon, and an oxygen. In this species down here, species C, the negative charge exists on a carbon, an oxygen, and an oxygen. And oxygen handles the negative charge better. So in species C, the negative charge can exist on 2 oxygens and 1 carbon instead of like species B, which has 2 carbons and 1 oxygen. This is most likely, without knowing any pK numbers here, this one is probably the most stable, which means it came from the most acidic, which means that this is the most acidic molecule here.